Implicit Neural Representation, INR, has gained significant attention due to its ability to characterize signals by preserving the mapping function from coordinates to attributes using neural networks. However, existing INR techniques suffer from spectral bias, where low-frequency components are more easily learned, and capacity-convergence gaps due to inadequate parameters initialization. To address these issues, the proposed Finer++ framework extends current activation functions to variable periodic ones, allowing for the supported frequency set to be flexibly tuned. This innovation is achieved by modulating the bias vector, or phase, of the variable periodic activation functions, thus enabling frequency tuning. The Finer++ framework is a universal extension of existing periodic and non-periodic activation functions to their variable periodic versions, improving the utilization rate of the definition domain. The proposed initialization scheme for Finer++ is proven to be effective and efficient from both geometric and neural tangent kernel (NTK) perspectives. The main contributions of this work include deriving and summarizing three characteristics of existing INRs, building a universal framework to improve INR performance, proposing a novel initialization scheme, and substantiating Finer++'s superiority over prior INRs. The concept of frequency specified spectral bias is introduced, which refers to the type of frequency determined by the chosen activation function and the supported set of frequencies determined by the empirical scale parameter. The capacity convergence gap in existing INRs is also discussed, where the function set that INRs can represent can be enlarged by increasing the initialization range of network parameters, but this violates the rule of guaranteeing convergence, resulting in a performance gap between theory and practice. Finer++ addresses these limitations by utilizing variable periodic functions for activating INRs, allowing for flexible frequency tuning and alleviating spectral bias and capacity convergence gaps. Experimental results demonstrate the effectiveness of Finer++ in various applications, including 2D image fitting, 3D signed distance field representation, 5D neural radiance field optimization, and streamable INR transmission, surpassing prior INRs activated with other functions. The Finer++ framework proposes the use of variable periodic activation functions to extend traditional activation functions, such as Sine, Gauss, and Wavelet functions, by composing them with a variable periodic function x equals sin omega f x plus 1 x, where omega f is a parameter controlling the overlap between different periods. This extension allows for the repetition of central nonlinear components and an increase in frequency along the z-axis. A novel initialization scheme for the bias vector B is introduced, involving a uniform distribution U, k, with a larger range k than traditional methods, enabling flexible tuning of the supported frequency set. The authors provide a geometrical perspective on the relationship between the supported frequency sets of Sine and Finer++, Sine, demonstrating that the supported frequency set f omega 0, k of Finer++ increases with the increase of the initialization range of B. The neural tangent kernel perspective views the training of the neural network as kernel regression, analyzing the diagonal property of the NTK or the distribution of NTK's eigenvalues to understand the convergence of the network on fitting signals. The NTKs of Finer++ are visualized, showing an enhanced diagonal property with the increase of the initialization range of the bias vector B. This property provides better shift invariance, allowing the network to learn the signal more effectively. Experiments demonstrate that Finer++ outperforms previous INRs in 2D image representation tasks, achieving higher PSNR values and exhibiting robustness to parameter selection. The framework's ability to capture high-frequency content in the input signal leads to a more accurate representation. Experimental results verify the effectiveness of Finer++ in various tasks, including 2D image fitting, 3D signed distance field representation, and 5D neural radiance fields optimization. The proposed Finer++ framework introduces a novel initialization strategy for implicit neural representations, INRs, enhancing their flexibility by allowing for tunable supported frequency sets. This is achieved by adjusting the initialization range of bias vectors in the network layers, enabling better representational ability and improved performance in various tasks such as image fitting and 3D shape representation. In image fitting, FINER++ outperforms state-of-the-art methods in terms of PSNR, SSIM, and LPIPS metrics, providing better visual results with clearer boundaries and fewer artifacts. For 3D shape representation, FINER++ achieves the best performance in terms of chamfer distance and IOU metrics, generating more detailed and accurate signed distance fields. Insights into the behavior of FINER++ under different initialization ranges and the role of the first layer in encoding frequencies are also provided, demonstrating the effectiveness of the proposed method. The NERF framework is employed to evaluate FINER++ for the task of learning a 5D mapping function that maps 3D coordinates and viewing directions to 3D colors and 1D opacity values. Experimental results using the wire protocol demonstrate the advantages of FINER++ for representing high-frequency components, outperforming 4 classical methods: PEMLP, Siren, Gaussian, and wire. The results in Table 3 and Figure 11 show that FINER++, Wavelet, achieves the best performance in terms of PSNR, SSIM, and LPIPS metrics, with an average improvement of 2.82 decibels in PSNR and an average increase of 0.040 in SSIM. The qualitative comparisons visually demonstrate the advantage of FINER++ for representing high-frequency components, showing more detailed textures and fewer artifacts compared to the other methods. The paper discusses the challenges of streamable INR transmission, which involves transferring INRs between devices with varying resolutions or providing streaming services that require progressively decoding different signal components while ensuring consistency with transferred network parameters. To address these challenges, Cho et al. Propose a progressive training strategy, which involves initially training a small, narrow network to model low-frequency components and then increasing the network width to capture mid-frequency and higher-frequency components. The authors argue that the Siren network used in this strategy exhibits a frequency-specified spectral bias, which limits its expressive power for modeling high-resolution signals under this training configuration. They propose the use of FINER++ in streamable INR transmission, as it is inherently suitable for building streamable INR, especially in cases where the signal has high resolution. The supported frequency set could be significantly manipulated by scaling the initialization range of the bias vector in the widened network parameters. The authors demonstrate the advantages of FINER++ over other INRs in image fitting, 3D shape representation, neural rendering, and streamable INR transmission. They also discuss future work, including designing INRs without any frequency-specified spectral bias. Additionally, the authors present a comprehensive overview of their research team's expertise and contributions to the field of computer science, specifically in the areas of computational photography, optimization for inverse problems, neural rendering, and Gaussian splatting. The team consists of researchers from various institutions, including Nanjing University, Northwestern Polytechnical University, and Vivo. The team's expertise also extends to numerical methods for partial differential equations and modeling methods driven by data and mechanism. Their work has been recognized with several awards, including the 2019 IEEE Broadcast Technology Society Best Paper Award, the 2020 IEEE MMSP Image Compression Grand Challenge Best Performing Solution, and the 2023 IEEE WACV Best Algorithm Paper Award. The author's research has also been influenced by various techniques and algorithms, including neural tangent kernel, physics-informed radial basis network, and marching cubes. They have also utilized various datasets, such as the Stanford 3D Scanning Repository, to validate their research.